we'll now look at direction fields. So now we're going to consider differential equations of the form dy dt equal to f of t of y. So f of ty means that we have this expression involving both the independent variable t and the unknown solution y. And if we actually display a solution of this equation in the ty plane, the differential equation simply says that at each point ty of the solution curve, the slope is given by y prime of t, which is f of ty. So a direction field is a picture that shows the slope of the solution set at selected points in the ty plane. So these are specific direction fields that you can see here. And like I said, it gives you the actual value of the derivative at each of these points. So for example, if I consider the equation y prime of t equal to t minus 3y plus 1, then I have small line segments with slope t times, with slope t minus 3y plus 1. And the line segment at a point P gives the slope of the solution curve that passes through that point. So along the t-axis, we can see that the slope of the line segments would be t minus 1, since y is 0. So they increase as we move to the right, and you can see along this line, they start negative, and then are getting bigger and bigger. They become 0, and then keep growing. As we look along the y-axis, so when t is equal to 0, we have negative y minus 1, so this means they're decreasing as we go up. And you can see they start positive, move to 0, and then keep getting smaller and smaller, negative. If we have the initial condition y of 0, 0, then we'll start at this point 0, 0 in my ty plane, and we just sketch a curve that follows the flow of the direction field. And at each point of the solution curve, the slope matches the direction field. Different initial conditions will give different solution curves. For example, if I start at this point, I just need to follow my lines. And now I would have this curve instead. This one gives the direction field for the equation y minus 1. So what are the initial conditions at t equal to 0? Are the solutions constant, increasing, or decreasing? So I want to know when this thing is constant. And basically what I'm looking for is whenever it's equal to 0, because a slope of 0 means it's not changing. So when y minus 1 is equal to 0, I have that y is equal to 1. And you can see that at 1, I do have this horizontal line. It's increasing when my derivative is positive, so when y is bigger than 1, and you can see everything above 1 is getting bigger and bigger. They are all increasing. It's decreasing when my function is negative, so when it's less than 1, and you can see that we are decreasing below 1. So this is the idea. We have this function. We're going to figure out when f of y is 0, when it's positive, and when it's negative. For example, y times y plus 1.5 for t greater than or equal to 0. So let's find our initial conditions as the resulting solution is constant, increasing, and decreasing. So this is the idea. To be constant, we need our derivative to be 0. So y plus 1.5 equal to 0. I would have y equal to 0, and y plus 1.5 equal to 0. So y equal to minus 1.5. When we're solving in polynomial inequality, I set up this number line, and then I'll pick points in each interval. A number smaller than -1 would be like -2, and if I stick in -2, I get -2 times -2 plus 1.5, which we can see is going to be positive. So it is positive between -infinity to -1.5. Between 0 and -1.5, we'll try -1. -1 times -1 plus 1.5. We'll see this is a negative times a positive, so it's negative. So this part is increasing when it's positive, decreasing when it's negative. Picking a number bigger than 0, 1 times 1 plus 1.5, we can see that this is going to be positive. So it's increasing again above 0. And here's the actual picture. We can see that at 0 it's constant because it's horizontal. The same thing at -1.5. Below -1.5, it's increasing. We see these lines going up. Between -1.5 and 0, you see the lines are going down, so they're decreasing. And then above 0, they are going up, so we're increasing again.